Hello and welcome back to this 12th lecture of the lecture series on principles of polymer synthesis. In this week, we have been talking about the principle of chain polymerization, and today's topic is the continuation of that. And if you recall what we had discussed in the previous class, we gave a general scheme of the how the radical chain polymerization proceeds. So, you have an initiator step, you have an initiation step, you have a propagation step, and then there will be a step in which you terminate these growing species. So, we ended our discussion in the last class on the different discussion after talking about different initiators that you could choose. You could have thermal initiators, you could have photochemical initiators where you dissociate say photochemically or thermally the initiator to produce the initiator radical. Remember, we are talking about radical polymerization only for the time being, and we could also have a redox process, oxidation reduction, that could create radicals. For example, a peroxide you could react with an inorganic ion, say Fe2 plus. In the process, Fe2 plus is oxidized to Fe3 plus, and the peroxide is reduced, and a peroxide radical is produced, which will be your initiator radical species. And we also told that for the time being we are going to concentrate on thermal initiation process and talk about the kinetic analysis, because the kinetic analysis will differ when you go to say photochemical initiator, so on and so forth. So, let us start our discussion now with the thermal initiation process, the kinetics of the reaction. So, the initiation process is something like this. You have an initiator, it dissociates say with a rate constant of Kd, d indicates your dissociation constant, dissociation process of dissociation. So, you have a bond breaking, let us say you have a peroxide, then it will create two species. So, we will write down this thing like 2R dot. So, this is initiating radical. Now, what will happen is that this radical will react with the monomer M. So, this is the initiation step. So, the initiation has two stages, one is the dissociation of the initiator, second is the primary initiation step. And let us say we draw the monomer like this M1 dot. So, this is the initiation, and then the next step is propagation. So, in propagation what you do is this M1 dot that is being produced, this is a chain initiating radical. This chain initiating radical can react with another monomer species with a rate constant of Kp, P being indicating propagation. So, propagation rate constant, it will be M2 dot. That M2 dot can react with M again to produce M3 dot, so on and so forth. So, in general your Mn dot will react with M to produce Mn plus 1 dot. So, you see that there is a growing chain. At the end of that chain more and more monomers are being added. So, this is a growing chain, say n number of M units are there, and at the end of this growing chain more number of monomer units are added. And one thing that you should notice here, that the rate constant for all these reactions I am writing Kp, Kp, Kp. This is also the actually a principle of equal reactivity. That means, whether the radical size is small or big does not actually affect the reactivity. So, whether your growing radical, that electron at the end of the chain, whether that growing radical is at the end of a small chain or a big chain, the reactivity does not change. That is to simplify your analysis, and it is also very close to reality what is found. So, this is your propagation, and finally, this radical has to be quenched in order to terminate this reaction, termination. So, when you are terminating the reaction, let us say you have a growing radical like this. There are two ways generally speaking, I mean unless you are considering other processes, we will come to that after, of terminating a growing radical. One way is that two radicals will come together like this, and they will terminate by coupling indicated by small k with subscript T C. So, termination by coupling of the two radicals. So, it will be CH2 CHY CHY, CH2. So, this is the end of the growth of the chain. So, this is a dead polymer. Okay. This cannot grow further because this does not have any radical center. So, this is how you can terminate a growing chain. So, this is termination by coupling, or what you could have is termination by disproportionation. What does that mean? You can have a radical like this, it is terminated on reaction with another radical. So, this wavy line indicates a long chain of some length through disproportionation. So, that will be Ktd. So, when you are terminating the growing radical through coupling reaction, basically you have this kind of scheme for the termination. So, you have a dead polymer that is formed, dead because the growing chain has been destroyed. The other process of termination is through disproportionation, and the disproportionation means, so this Ktd is the rate constant of this disproportionation. So, T is the termination and D is termination through disproportionation. What will happen is that one of these hydrogens will be abstracted by this radical that goes here, and then you have a double bond that is produced here. So, ultimately the product will be something like this, CH2 CHY, and this hydrogen is shifted here. So, this radical is scavenged, and then this species will be converted to CYH double bond CH2. So, this is termination through disproportionation. So, you can see there that when you are terminating through coupling, two propagating species are coming together to form one final chain. When you are doing a disproportionation coupling, when you are doing a disproportionation termination through disproportionation, two propagating species are coming together to produce two polymer chains. So, this particular observation will be important later on. So, in general the termination process you can write as Mn dot plus Mm dot. When you have termination through coupling, you have Mn plus M dead polymer. When you have termination through disproportionation Ktd, you have basically Mn plus MM. Now, this termination rate constant typically they are of the order of 10 to the power 6 to 10 to the power 8. So, that will be around 10 to the power 6 to 10 to the power 8 liter per moles per second. Importantly, the propagation rate constant is of the order of 10 square to 10 to the power 4 liter per mole per second. So, if you look at these two values, you can see that for the termination reaction the rate constant is orders of magnitude higher than for the propagation reaction. So, you might be asking this question, then why the propagation will happen at all? The chain will terminate at a very small chain length. So, high molecular weight should not be reached because the propagation rate constant is orders of magnitude 2 to 3 orders of magnitude, even more sometimes 4 orders of magnitude lower than your termination rate constant. But the reason why the propagation happens is because the first thing is that the radical concentration, the growing radical concentration is very low, is of the order of 10 to the minus 8 molar, because the termination, the rate of termination is nothing but rate constant of termination into m dot square, m dot being the identity of two different radicals which are coming together. And why it is m dot? So, because we are not saying it is Mn or Mm, it is two radicals that are coming together, and it is square because the two concentrations are involved, and Kt is in general the termination rate constant. So, this m dot is very low. So, that actually counterbalances, that is one thing, and the second thing is the rate of polymerization itself of course, it decreases with increasing kT, but it does so in this kind of proportion. So, only with kT to the power half. So, the rate of polymerization is affected not as much as would be expected if it was 1 by kT. So, that half factor is there. So, these are two of the reasons why you can still get very high molecular weight of the polymer even when your kT is orders of magnitude higher than Kp. Now, you might be thinking I am writing kT here and not KTC or KTD, because you might in actual situation when you are terminating a growing radical, you might terminate it through coupling or disproportionation. It is a combination of the two that are working in actual scenario. So, some fraction of the radicals are being terminated through coupling, some fraction is being terminated through disproportionation. Considering there is no other process of termination, let us assume that for the moment. So, in that case your kT is basically equal to A into KTC plus 1 minus A into KTD, where A is the fraction of termination through coupling and 1 minus A is the fraction of termination through disproportionation. That is 1 minus A, because we have assumed that there is no other process that is operating for termination. So, A is the fraction of termination through coupling and 1 minus A is the fraction of termination through disproportionation, and we are assuming 100% of termination is either through coupling or disproportionation together. There is no other process in which the termination will occur. Okay. Now, of course, the assumption here is also your Kp and Kt, they are independent of the radical size. So, if you look at the rate of monomer disappearance, which is the rate of your reaction, that is nothing but equal to rate of initiation plus rate of propagation. Initiation step has two stages, I told you. Your initiator species is in the first step dissociating, in the second step the dissociated species, which is your initiating radical, that reacts with a monomer to produce M1 dot, which is your chain initiating species. So, that Ri encompasses both the reactions and Rp is the rate of propagation. Now, this actually can be approximated to be equal to Rp, because Rp, rate of propagation, is much higher than the rate of initiation, simply because the number of monomers that are involved in the rate of propagation are exceedingly large. Lot of monomers are being involved if you compare with the rate of initiation. So, this is approximately equals to Rp. So, the rate is then Rp. So, what is Rp? Rp is nothing but your rate constant into m dot into m. So, recall this propagation step here. So, Rp, the rate of propagation, is equals to rate constant into your monomer concentration into m dot. That m dot actually includes the total concentration of all the radical species present there. That is why I am putting m dot and not mn dot, because mn dot actually identifies the species. M dot means summation of all the radical concentrations. So, this is m dot into m. So, total concentration of chain radicals. Now, this m dot, we have to find an expression for that, experimentally measurable quantity. So, let us then apply a concept which is called steady state concept, steady state assumption. The steady state assumption means the concentration of radical, although it is very small, the concentration of the radical remains constant throughout the reaction, that is the steady state assumption. So, that would mean the rate of initiation is equal to rate of termination. That means the rate at which radicals are being produced is equal to the rate at which the radicals are being scavenged. That means the total radical concentration at any point of time in the reaction system is constant. So, if it is constant, then Ri equals to Rt. Now, Rt is nothing but Kt into m dot square, because two radicals are coming together, whether it is coupling or disproportionation, two radicals are coming. So, m dot plus m dot, and then you have a dead polymer. Either you have two chains forming because of disproportionation, or you have only one chain of the dead polymer forming because of coupling. So, Kt into m dot square, Kt being the rate constant of termination. It actually takes into account both the coupling as well as disproportionation part. So, from here your m dot is nothing but Ri divided by Kt to the power half. Now, what is Ri? Ri, that is rate of initiation, is f kd into I. This needs some explanation. So, you have your initiator species that is dissociating with a rate constant of kd, this is dissociation rate constant, and it is forming 2 R dot, and in the next stage this R dot is basically reacting, this is Ki with a monomer to produce M1 dot. So, these are the two steps for initiation. Now, the first step here is the slowest step, and in this particular reaction system then you have to only consider the first step, because the slowest step is the rate determining step. So, that is why the rate of initiation, which encompasses both the reactions, is nothing but equal to your dissociation constant into I is an initiator concentration, and then there is a term F. This F is nothing but efficiency of the initiator or the initiator efficiency, initiator efficiency. So, why not initiator efficiency being is 1, why it might be less than 1, that is why you are putting F. Efficiency either it is maximum, which case it is 1, or it could be less than 1, say fraction of that, say 0.8, 0.7, which means the total of the initiator that is dissociating, all these radicals that are being produced, the initiator radicals that are being produced through the dissociation of the initiator, all of them do not initiate new polymer chains. A fraction of them initiates new polymer chain, that fraction is called the initiator efficiency. If all the radicals, all the initiator radicals that are being produced by the initiator species, all of them, each of them initiated one radical, one polymer chain, then the fraction, then the efficiency of initiation will be 1, but some of them do not initiate new polymer chains. So, the efficiency decreases. So, you know, you can just take an example of that. Say, let us say you have a growing polymer chain which is Mn dot, and let us say you have benzoyl peroxide, phi being benzene ring, as the initiator. So, what can happen is that this benzoyl peroxide can react with this growing radical chain in this way. It can actually destroy that radical, and that radical is being transferred here. This is actually a process called chain transfer. So, this growing chain is being transferred from this species to this species, and then it will form something like this. So, in normal situation it will form 2 of the benzoyl radicals, but here it is actually forming one benzoyl radical like this, and this growing polymer chain is terminated. Now, this benzoyl radical now that is produced, it can of course initiate another polymer chain, but the problem is if you take one of these initiator molecules, it should actually create 2 radicals like this. If each of these radicals initiates one polymer chain, then the efficiency will be 1, but actually this molecule, if you are considering, this is terminating this Mn dot, growth of Mn dot. So, this molecule is giving in effect one radical which is incorporated into the growing polymer chain. Let us say it is starting another polymer chain. So, let us say it is starting another polymer chain by reacting with M, and then it will be M1 dot. This will be incorporating this unit at the end. So, this is M. So, that means all the potential radicals that could be produced from this initiator, all of them have not been used to generate or initiate a fresh polymer chain. That means the efficiency is less than 1. This is a very, this is one of the ways in which the efficiency could be less than 1. There are other ways also. I am just giving you one example. So, your Ri is equals to F Kd into I. Now, if you are considering all these expressions here, so your Ri is nothing but equal to F Kd into I, and your M dot was Ri divided by Kt to the power half. Just recall here, your M dot was Ri divided by Kt to the power half. So, your M dot is nothing but F Kd I divided by kT to the power half. You use these two equations. Now, previously we have shown your Rp, this expression we have drawn, Rp equals to Kp into m dot into m. So, we are trying to find an expression for m dot which is in terms of measurable parameters. So, this m dot is nothing but this, and this can be replaced with this. So, ultimately your Rp which is Kp into m dot into m, that becomes equal to Kp into m into f Kd I divided by Kt to the power half. So, you can immediately see your Rp is proportional to 1 divided by Kt to the power half. So, of course, when Kt goes up, that means the rate constant for termination when it is high, your Rp is low comparison. I mean, if your Kt goes up, correspondingly your Rp goes down, but it does not go down if you compare, say for example, if it was a situation where Rp was proportional to 1 by Kt. Since it is proportional to 1 by Kt to the power half, it does not go down that alarmingly. And as I told previously also that is one of the reasons why even if Kt is much higher than Kp, orders of magnitude higher, still you will have propagation and not termination as the overwhelming factor that will limit the molecular weight of the polymer in general situations. Okay. So, this expression that we have now derived is very, very important. We will keep coming back to it after. So, let us also then write down this expression once more here, Kp into m into f Kd I divided by Kt to the power half. This is the expression. Now, let us come to the concept of molecular weight. We will correlate these things after for this growing, so for this radical polymerization. Molecular weight, of course, it is related to your xn bar, number average molecular weight, and that number average molecular weight is related to a term called kinetic chain length. So, we define a term called kinetic chain length here, say nu. This kinetic chain length is average number of monomer, let me write it down and then I will explain, molecules consumed per radical that initiates a polymer chain. So, what is the average number of molecules that is being consumed per radical that initiates the polymer chain? Say one radical is initiating one polymer chain. So, per polymer chain that is being initiated by one radical, how many monomer molecules have been incorporated into the chain? So, remember that before the termination can occur, your polymer chain is not complete. So, it has some radical at the end. Once the termination has occurred, you have got the polymer and correspondingly the molecular weight. So, if you just consider that you have only coupling or disproportionation for the termination process, there is no other process involved in the termination, reasonably assume that this kinetic chain length is basically related to your molecular weight, because it is nothing but, so let us say the degree of polymerization is nothing but the average number of structural units per chain, and here you are saying the average number of monomer molecules that have been consumed to create the chain that is being produced per radical. So, this is your kinetic chain length. Under certain conditions it may be directly equal to your average number of average degree of polymerization, number average degree of polymerization, or it may be having some factor with it. So, we will come to that in a little while. So, your nu, which is your kinetic chain length, is nothing but then rate of polymerization divided by rate of initiation, if you go by this definition. Now, rate of initiation is nothing but equal to rate of termination, steady state assumption. So, you have Rp is Kp into m dot into m divided by Rt, which is Kt into m dot square, and then you put this expression of m dot here. You know what is m dot? M dot is nothing but this part. So, you put that value of m dot here. So, things are related that way if you have a look at it. So, one of the m dots are going. So, you have k p into m divided by k t into m dot, and that m dot is nothing but f k d I to the power half divided by k t to the power half. So, if you compare these two, then the k t to the power half comes down. So, your nu is equal to k p into m divided by f k d k t I to the power half. So, from here intuitively you can understand, if your kinetic chain length is higher, your molecular weight might be higher, because then there will be a more number of monomers on an average in a particular chain. And strikingly, if you look at this particular equation here, if your initiator concentration is growing, then your kinetic chain length basically is decreasing as a function of 1 by I to the power half. So, if you are trying to increase the rate of polymerization by increasing the initiator concentration, that you can increase of course, because your Rp is proportional to I to the power half. So, if you increase the initiator concentration, your rate of polymerization increases. But if you do so, then what you will have is that if you increase the initiator concentration, correspondingly your kinetic chain length will decrease. So, the molecular weight will decrease. So, the conclusion here is that if you are trying to increase the rate of polymerization by simply increasing the concentration of the initiator, your kinetic chain length will decrease, and if your kinetic chain length decreases, correspondingly your molecular weight will also decrease. So, in the process of increasing the rate of polymerization, you will actually compromise your molecular weight. Now, how this molecular weight is related to this degree of polymerization? Now, we will come to this important question. So, number average degree of polymerization is equal to 2 nu, nu is the kinetic chain length, when the termination is through coupling. This is not difficult to understand. You have two growing chains and they are terminating through coupling. So, if they are terminating through coupling, the two growing chains become one chain. So, basically one growing chain kinetic chain length nu, another growing chain kinetic chain length nu. I mean both are nu because this is an average kinetic chain length. So, this is average number of molecules per chain. So, that is kinetic chain length is nu. So, both of them come together. So, then ultimately how many number of molecules on an average, the monomer molecules on an average on the chain, that is 2 nu. So, that will be your number average degree of polymerization. So, your xn bar equals to 2 nu. However, if you are doing only through disproportionation the termination, then your xn bar is only nu, because two chains have come close by for termination, and at the end one hydrogen is abstracted from one of the chains, goes to the other one, both the radicals are destroyed. So, two chains you start with nu and nu kinetic chain length, at the end you get only two chains, not one chain. So, each chain corresponds to the average molecular weight xn bar. So, then each chain has a nu kinetic chain length that will be equal to then the number average degree of polymerization. So, if you have termination through only coupling, then your number average degree of polymerization is equal to 2 times the kinetic chain length. If you have termination through only disproportionation, then your number average degree of polymerization is equal to kinetic chain length. So, question is, how do we know the mode of termination? How do we know if we are having termination through disproportionation or coupling? This particular question is also related to the efficiency of initiation. We will come to that after, because when we told about this efficiency of initiation, we did not talk about how we can find it. So, we will do a problem right after we finish this particular exercise here, and then we will correlate. That time we will not have today, but we will conclude today with a direct correlation, in general correlation of degree of polymerization with kinetic chain length, a general correlation, and how the coupling, the proportion of coupling and disproportionation is related to that. And we will show later on in the next class that this is something that is related to your, you can actually correlate in a particular problem, you can actually correlate that and try to understand a way in which you can find the efficiency of the initiator. So, let us say you have n number of propagating chains, and let us say the termination for this particular system happens only through coupling or disproportionation. Now, remember when you have coupling, two chains are coming together and each chain, so your initiator is basically producing two fragments. One initiator is producing two fragments, R dot plus R dot, I told you, because the dissociation of the peroxo linkage, say, so two peroxy radicals. So, two initiator fragments. So, the chain that is being produced, if it contains two initiator fragments, chain, that means final polymer chain, on an average if it contains two initiator fragments, what does that mean? This means the termination has predominantly occurred through coupling, because each growing chain that is being produced by one initiator fragment, that is one R dot, it started the initiation of one chain, that means that R dot is at the end of that chain. So, that each polymer chain will have, not each polymer chain, each growing polymer chain will have one initiator fragment. So, basically if you are taking two growing chains, each of them has one initiator fragment. So, and these two initiator fragments could have come from one initiator molecule, it dissociates in two fragments. So, now these two chains, if they scavenge the radical or if they terminate through coupling, then these two chains become one chain. So, ultimately the polymer chain that will produce on an average, that will have two initiator fragments from two growing chains. And if you do disproportionation as the main process of termination, say 100% disproportionation, then two growing chains, they will end up as two full grown polymer chains, final, no radical present. So, that means each growing chain had one initiator fragment. So, ultimately the chain that you will produce, the polymer chain that you will have on an average will have one initiator fragment. So, experimentally if you can find out this thing by some means, that on an average how many number of initiator fragments are there in the prepared polymer molecule, then you can have an idea about the extent of disproportionation or extent of coupling. So, we will come to this problem directly in the next class and continue thereafter. Till then, goodbye and thank you.